Okay, so we've looked at how if you put a wire with current going through it inside a magnetic field, the wire will experience a force which will make it move. And that's the basic principle on which a motor works. So all that we've got to make a simple motor is a coil of wire inside a magnetic field, and we have some little slightly complex apparatus down here. But basically this is here to make sure we get current flowing through our coil in the right kind of direction. And the best way to understand how it works is to think about one half of the coil. Let's concentrate on just this part of the coil here. This bit here, where the current's coming this way, coming back towards the cell down here. Okay, so we've got current flowing around in positive, and I'm going to concentrate on this bit where it's coming back this way. Well, we've got a magnetic field from north to south, and we've got current coming this way. So if you get your left-hand rule, field goes from north to south, current coming towards us. That means that this half of the coil is going to experience an upwards force. And if you can get your left hand to work over here, you can work out, or you can just guess, that this side, because the current's going in the opposite direction, this side is going to experience a downwards force. We've got what we call torque, or a couple, or a pair of forces which are going to cause this coil to spin. And so we've got the start of an electric motor. But there's a problem, because if you think about this pair of forces, as they spin the coil, once we get to the coil being vertical, this force will be pulling upwards, this force will be pulling downwards, the coil is going to stop. It's going to reach vertical, maybe wobble around a little bit and get stuck there. So how can we keep the coil spinning? Well, that's where this little device down here comes in. As we get to the top, what we really want to do is flip the forces over, so that this side of the coil gets pulled upwards to the top, and then it gets pushed down this side, and then pulled up this side, and then pushed down this side, pulled up this side, pushed down this side. So what we need is a way of making sure that when we get to the top, the forces swap over. Now, how can we do that? Well, think again about your left-hand rule. If you want to swap the direction of the force, you've got to swap the direction of the current. Okay? I mean, you could swap the magnetic field, but that's going to be pretty complicated. And that's essentially where this little device down here comes in. If you look, we've got two little bits of metal, we call that a commutator. A split ring, essentially, the two halves of a metal ring, a commutator. These contacts here are called brushes, maybe made of graphite or something like that. And they're there really to make sure we have a full electrical circuit, but we have to allow this ring to spin, otherwise the wires would get tangled up if we didn't have this arrangement. So you can see that the ring can sort of brush against the brushes and keep spinning without the wires getting tangled up. So that's one of the reasons we have the commutator. And the idea of the split ring bit is that, as I said, I want to be able to switch over the direction of the current when this bit gets to the top. And it's quite simple to do, because at the moment this half of the coil is connected to the negative terminal down here. It's the negative terminal of this cell. It gets to the top, this half of the split ring will now connect to this brush, which is connected to the positive. So suddenly when I get to the top, instead of having current going this way, it'll switch over, connect to the other terminal, and the current direction in this half will reverse, and this half of the coil will start getting pulled down. So all this is doing is it's swapping the direction of the current every half turn in order to keep the coil spinning in the same direction. A few other little points about the electric motor. The size of this force depends on the strength of the magnetic field. So I could make a stronger, faster motor if I had a stronger magnetic field. I could also make it stronger if I put more current through. Again, I'd get a bigger motor force. If I had more coils of wire, or if I put an iron core in the middle, that would intensify the magnetic field. Again, you get a faster, more powerful motor. One final point about the motor: as it stands, it's a very simple construction, Because the magnetic field is going across, we don't get a very smooth kind of motion. A more practical design for a motor that's used for industrial purposes would have curved magnetic fields, curved magnetic pole pieces around the outside, which create this nice magnetic field which is symmetrical, coming from all directions, and you get a much smoother motion. You might also have multiple coils wound in different directions to make sure there wasn't any inconsistency in the variation of the size of the forces. So that's the simple DC motor.